the future of fossil fuels, it can be projected with some amount of reason by sort of extrapolating from what is going on today and how we think things might change into the future. There are lots of different ways that you can do this sort of scenario forecasting, some of them very complicated that take into account individual countries and individual situations. But you can also get there from a broader perspective using this formula, which is known as the Kaya identity. It takes the rate of carbon emission can be calculated as the product of the population, as you expect it to grow in the future, times the GDP per capita, because fossil fuel use is so closely tied with economic activity. And if we look at the units that we're building up here, population is people, GDP per capita is dollars per person per year. And so the units of people cancels out there. The third term is the energy intensity. And so this is basically how much energy it takes to make a dollar, to do a dollar's worth of economic activity. And this depends on whether you're making a dollar's worth of steel or a dollar's worth of coffee or something like that. It makes a difference. It depends on energy efficiency. So now we've got watts per year. The last term has to do with this energy source, how you're making the energy. The amount of carbon per watt of energy. So nuclear power would have less carbon per watt than coal production. The units now cancel, so we have watts or gigatons of carbon per year. So extrapolating the present day trends in these terms, we need to guess how high we think Earth's population is going to plateau at. Hopefully it will plateau and stop growing. It looks like it's doing that. The average income on the Earth is increasing as a function of time. So we can put the rate of change of that into the equation. The energy use is getting more efficient, so the energy intensity is decreasing through time. And then there are also changes in the carbon source that have to do with efficiency, but also there's been a recent trend away from coal because of lower prices for natural gas brought about by improvements in the ability to extract natural gas, known as fracking. But you put all these things together and you end up with the projection that under business as usual, that means with no effort to avoid climate change, the rate of carbon emission today, about 10 gigatons a year, could grow to about 20 gigatons a year by the year 2100. So the human impact on the Earth's carbon cycle is to dig up some of the carbon in the solid Earth reservoir and put it in the atmosphere at a rate of about 8 gigatons per year. And also, we are cutting down trees on land, which results in a flux of CO2 to the atmosphere of about another 2 gigatons a year. Now, the concentration, the amount of CO2 in the atmosphere is going up, but it's actually not going up as quickly as it should be given how much carbon we're putting into it. It's only going up at about 4 or 5 gigatons per year. So there's a whole bunch of carbon that we're putting in the atmosphere which is not showing up. It's going away into some combination of the land and the ocean. We know that the time scale for the solid Earth to take up carbon is very, very long, so that's not really helping us that much, presumably. It's hard to know how much is going in, hard to measure how much is going into the land because the land is so heterogeneous. One tract of forest is very different from another, and to know exactly how much carbon is being absorbed is very difficult measurement to make. Actually, interestingly, they can measure the carbon uptake into the ocean much more easily, much more precisely. So in the early days of thinking about this, back in the 1950s and before, people basically figured that the ocean would control the atmospheric CO2 concentration, and that we wouldn't really be able to change atmospheric CO2 because the ocean, after all, has 70% of the Earth's surface, and it's also got a lot more carbon than the atmosphere does, about 40 times more. And so it's a really heavy hitter in the carbon cycle. The reason why the ocean doesn't just immediately mop up all of our extra CO2 has to do mostly with the fact that the way that the ocean water circulates, the way it moves from the surface where it can see the atmosphere down into the deep, which is where most of the ocean water is. The way the ocean circulates is that in the high latitudes, in Antarctica and in the North Atlantic, where it gets very cold, the water at the surface gets cold enough that it can sink by the same sort of convection process we were talking about before, but now upside down because we're cooling it from above. And so you have this very focused downward flow in very specific locations, and this is balanced by sort of vague and diffuse upward velocities every place else or other parts of the ocean. The overall time scale for the circulation of the ocean is about 1,000 years, and that actually limits how quickly the CO2 can equilibrate between the atmosphere and the ocean. When CO2 dissolves in seawater, it does some interesting chemistry. And this is the same chemistry that goes on in our cell plasma and in our blood. The CO2 reacts with water now, which is what it did for photosynthesis, but that was a totally different reaction. This is just an abiological chemical reaction where you join those two molecules together and make a carbonic acid, H2CO3. So if you figure out the oxidation state of the carbon here, it's the same as the oxidation state was here, because adding an H2O, you get -2 for this and +2 for that, and so it balances. It's the same. We're not changing the oxidation state, so it doesn't take energy to do this reaction. It just happens all by itself. So carbonic acid is called an acid. A chemical is called an acid if it can release H pluses to the water. So a solution, a water solution that has a high concentration of these H pluses, these protons, is what they call an acidic solution. And it's the reason why we mention it at all is because H plus is a very aggressive chemical. If you spill acid on your skin, you'll burn yourself because the H plus can react with the molecules in your skin. It can dissolve the threads in your pants, that sort of thing. So this carbonic acid is actually what they call a diprotic acid because it can release first one and then a second H plus. So this is bicarbonate, like baking soda is sodium bicarbonate, and this is carbonate ion, has a charge of -2. So how this chemistry works is kind of complicated, and it can be best understood by writing the chemical reactions in a way that don't just sort of vaguely slough off these H pluses, because there aren't that many H pluses in solution. It's not like some infinite slush fund that you can just throw stuff into as much as you want to. Actually, the best approximation is to write these reactions where it's not changing the H pluses at all, because there's so much more carbon than there is H plus. So writing the reaction in that way, we have CO2 plus this carbonate ion and a water on one side, and on the other side, we have two of these bicarbonates. Now, this is an equilibrium chemical reaction, which we can apply an idea known as Le Chatelier's principle to. Le Chatelier's principle says that if a system is in equilibrium and then you perturb it by adding some chemical on one side of the reaction, it will push the reaction in the other direction to try to minimize the imbalance that you've created. So if you add CO2 to this, what happens is it consumes this carbonate ion and shifts more toward the bicarbonate. So it's as though the carbonate ion here is sharing one of its 2- charges with the CO2. So the importance of that is that these guys that have electrical charges, they're called ions. An ion can't evaporate into the air. There are no ions in the air because they're just not stable. You can find them in water because the water allows it to form, but not in the air. So by lending one of its negative charges to this CO2 to make a bicarbonate out of it, the carbonate is essentially hiding that CO2 from the atmosphere. So the existence of this chemical reaction allows the water to take up more CO2 than it would if there were no such chemistry. Turns out there's 10 times more of this carbonate ion than there is dissolved CO2 in water. And so that means that the buffer strength, the ability of the water to take up CO2, is 10 times stronger than it would be if this chemistry didn't exist. So oxygen, for example, or nitrogen, those are gases. They can dissolve in water, but they don't do any of this wondrous pH chemistry. And so they don't have this buffer. They don't have as much ability to take up those gases as CO2. So the depletion of the carbonate ion by this buffer chemistry is what's known as ocean acidification. So when you acidify the water, you have less of this carbonate ion. And this is actually the part of the acidification that has the strongest impact on the biota of the ocean. Especially critters that make calcium carbonate shells, like corals, or there are little plankton that have shells of calcium carbonate. So looking at this chemical reaction as an equilibrium again, you could imagine that if some process takes out carbonate ion, this calcium carbonate is going to dissolve to replenish that carbonate ion. So it's sort of paradoxical. You look at a coral reef and it's a big chunk of stuff made out of carbon, and you would think that putting more carbon into the system would make that chunk grow bigger. But actually, because of this pH chemistry, it makes corals dissolve. So they can measure how much CO2 is invading the oceans by a variety of different techniques. You can just go out and measure the concentration of CO2. And of course, there's a lot of dissolved carbon already in the water. So it's a tricky question to distinguish the tiny fraction of that is new carbon that invaded the ocean from fossil fuel combustion. But it can be done. Or there's a very clever method that I wanted to show you that involves measuring simultaneously changes in atmospheric CO2 and also oxygen. So when you burn fossil fuel, it's just like respiration, it consumes oxygen. And so the CO2 concentration goes up and the oxygen concentration goes down from that process. But then there are two different possible fates of that CO2 that we're trying to distinguish here. One is that it could get taken up by trees on land by some sort of photosynthesis, and when that happens, it releases oxygen. The other possibility is that it can just dissolve in water, and then it does this buffer chemistry, but it doesn't immediately get turned into photosynthesis. It doesn't produce oxygen. So if you compare the rate at which CO2 is rising with the rate at which oxygen is falling, you can sort of decide how much of the carbon is going into the land biosphere versus how much is into the ocean. So the bottom line is about 50-50. There's about 2 gigatons a year going into the oceans, and they can measure that by multiple methods, and they get the same answer by the different methods. So we have confidence in that. And then just by difference, by balancing the budget, there has to be an uptake going into the land of about 3 gigatons a year of carbon. And this is dicier because we don't know where that is. We're still trying to figure out, even though it's a massive amount of stuff. But it's just harder to find on land. Anyway, the bottom line is that to a large extent, the ocean and the land are helping us out by absorbing fossil fuel CO2.